The Interested Reader podcast is about exploring the world beyond the textbook. We'll cover many lessons in math, physics, and astronomy, and then delve into the mysteries of the universe. Physics is fun, people just don't know it, and I want to change that. I want to spark your curiosity about the world around you and ignite your passion for exploring and questioning. I'm your host, Sarah Tyke. Come with me and let's take a random walk into the world reserved for the interested reader. Hi everyone, welcome to Physics Explained by the Interested Reader. This is part of our video lesson series, and today we are going to start talking about motion in 2 and 3 dimensions. So we're going to break this up into a couple lessons. The first thing we're going to have to talk about is vector notation and unit vectors. So in order to talk about most quantities in physics, we have to talk about vectors. And we know from a previous lesson that vectors have both magnitude and direction. So we'll just reminder here that a vector needs magnitude, which is also the size of it, magnitude, and direction. The opposite of that is a scalar, which is just a magnitude. So we talk about quantities of position and displacement. And these are both vector quantities. And so we're going to be using unit vectors when we talk about position and displacement. So first of all, we're going to have our coordinate system. And I'm going to try to do a 3-dimensional coordinate system here. So in our 3D coordinate system, X will be coming, what would be kind of out of the page here, the way I've written it. Y will be going left to right, and then our Z-axis will be going up and down. So positive directions will always be to the right and up in our standard coordinate system. So in our system, we would draw a position vector. And I'm going to call this R1. And to denote a vector, we're going to put a little arrow over the top of that R so we know it's a vector. And that would be a vector relating to a point that would be at a coordinate x1, comma y1, comma z1. So whenever you're going to give a position of a point in a 3-dimensional system, it's going to be given by x, y, z. And we'll draw another vector. We'll call it R2. So it's an R sub 2. Again, we're going to put the arrow over the R to denote a vector. And this point is going to be at a position x2, comma y2, comma z2. So we've got 2 position vectors, 2 coordinates. And then the new thing that we're going to add here is going to be called a unit vector. So I'm going to write that in red. And a unit vector is just a short vector. It has a unit length. It's exactly one unit in length. So along the x-axis, it's going to be called I, with a little triangle over the top called a hat. So it's I hat. Along the y-axis, it's going to be called j hat. And along the z-axis, it will be called k hat. So those are what we call unit vectors. I hat, j hat, and k hat. So they are vectors. They indicate a direction along an axis, and their magnitude is 1. So they won't change the value of your vector or your numbers at all because it is just a unit of 1. Okay. So now we're going to write our vectors R1 and R2 with our vector notation. So R1 is going to be its x1 position in the I hat direction plus y1 in the j hat direction plus z1 in the k hat direction. So because r1 is a vector, it has to have magnitude and direction. So the magnitude is our x, y, and z components. That gives us the magnitude. And then the vector portion is our unit vector. So the I, j, and k hat gives us the direction portion. So that is how we would write a vector in our three-dimensional space. Okay, so I am going to erase our coordinate system, and we're going to start working with R1 and R2. So we said R1 is x1 I hat plus y1 j hat plus z1 k hat. R2 is going to be the same setup. It'll be x2 I hat plus y2 j hat plus z2 k hat. Now the displacement is going to be the change in r, which is going to be r2, these are vectors, minus r1 vector. Okay, so this is displacement. And that change in r is also called delta r. So when we're going to substitute in our equations for r2 and r1, so that would give us x2 minus x1 in the I hat direction plus y2 minus y1 in the j hat direction plus z2 minus z1 in the k hat direction. I'm sorry I had to write this kind of vertical. It's too long of a vector to write out in one line. Hopefully this translates. So we've kind of talked about this before when we talked about delta quantities or changes in quantities, where it's just your final position or your final quantity minus your initial quantity. It's the same thing we're doing here. But because we have a vector, we have to deal with these unit vectors, the I, j, k hat. And then when you're talking about this change in displacement, you're just going to take the magnitude of each of your directions. So the x2 minus x1, it's that change. And then your change in y, which is y2 minus y1. And your change in z, z2 minus z1. So that gives us our change in displacement, or our change in r. So the next thing we're going to talk about will be velocity. So I'm going to go ahead and erase all that. So remember, velocity is also a vector. And when we talk about velocity, we've got average and instantaneous velocity. So first let's talk about our average velocity. So we're going to have our vector v for velocity, and I'm going to put a bar over the top of that to denote average. There's a lot of notation here. If you're seeing this in a textbook, it would just be a bolded v. Since I can't bold it, I have to put the arrow over the top. So average velocity is just going to be your change in displacement, that delta r, as a vector, divided by delta t. So this is kind of similar to how we had in one dimension. We had our velocity v was delta x over delta t. So now we just have three dimensions that we have to deal with. Okay, so delta r is going to be a change in x in the I hat direction, plus our change in y in the j hat, plus change in z in the k-hat direction. And then all that gets divided by delta t, change in t. So I'm just going to kind of rewrite this. We're going to distribute that t along each of our quantities. So we have delta x over delta t in the I-hat direction, delta y over delta t in the j-hat, plus delta z over delta t in the k-hat. So that would be our average velocity written in our vector notation. And just like when we talked about our one-dimensional velocity, we can talk about instantaneous velocity. And it is the limit. We'll write this down here. So the instantaneous velocity is the limit of our average velocity as our quantity delta t goes to 0. So when there's no change in time, it's at this exact instant in time right now. So as delta t goes to 0. And what this means for us is that we're going to be taking the derivative, or we're going to write it as a derivative. So I'm going to go ahead and erase our average velocities here. Most of the time you're going to be talking about instantaneous velocity when you're going to be using derivatives. So in this case, our instantaneous velocity of our vector v would be dr over dt. And we're going to substitute in our position vector. We're not going to worry about 1 and 2 anymore because, again, 1 and 2 means there's a separation in time between position 1 and position 2. We're saying there is no separation of time anymore. It's instantaneous. It's right now. So R1 and R2 are the same thing. So we don't need to worry about our subscripts. We're just going to do the derivative of vector r with respect to t. And it looks like this. So we're going to write d over dt. Again, you'll hear derivative notation said d by dt. d by dt of vector r. So that's d over dt of x in the I-hat direction plus y in the j-hat plus z in the k-hat direction. And again, we can just distribute that derivative through. So we have dx dt in the I-hat plus dy dt in the j-hat plus dz dt in the k-hat direction. So that would be our velocity written in vector notation. And our last thing we're going to talk about is going to be acceleration. And acceleration is also a vector. So we can also talk about average and instantaneous acceleration. So we're going to do very much the same thing. We've got average is going to be our a with an arrow to indicate a vector. With average, we put a bar over the top. And that is a v2 vector minus v1 vector divided by our change in t. So we would go through the same thing that we did before with our subscripts, our velocity. I should write this down here. Remember, our velocity was Vx. Oh, I'm sorry. Dx dt in the y direction plus dy dt in the j direction plus dz dt in the k direction. So that was our velocity. I'm just going to rewrite each of these derivatives in terms of velocity. So dx dt is our velocity in the x, is the x component of velocity. So we write that as v sub x. dy dt is the y component, so it's v sub y. dz dt is the z component, and that's v sub z. So our velocity now becomes vx in the I hat direction plus vy in the j hat direction plus vz in the k hat direction. Okay. So now we have a position vector where we're doing our x, y, z in the k hat, in the I, j, k directions. We have our velocity, which is vx, vy, vz in the I, j, k hat directions. And now we will do our acceleration. So with acceleration being v2 minus v1, it's going to be the same thing that we did before. And then we're going to do instantaneous acceleration, which is just, again, it's a derivative. So instantaneous velocity is a derivative of position. Instantaneous acceleration is a derivative of velocity. So instantaneous acceleration is a derivative of velocity with respect to t. So we're just going to go ahead and write that down. So we have acceleration is dv dt. So it's the same principle. We have vx in the I hat plus vy in the j hat plus vz in the k hat, and we would take the derivative with respect to time of that quantity. So we have dvx dt in the I hat plus dv dy by dt plus dvz by dt in the k hat. And similarly with our, as we had with velocity, dvx by dt is the x component of acceleration. It's the derivative of velocity in the x direction. The derivative of velocity in the y direction is the y component of acceleration, so it's a sub y. And derivative of velocity in the z direction is the z component of acceleration, a sub z. So our instantaneous velocity would be written as our acceleration x component in the I direction, the y component in the j direction, and the z component in the k direction. Okay, so that's all we're going to do for today. It was just to introduce you to vector notation, this idea of unit vectors, because you will see unit vectors come up. Most of the time, once we get past this information or the unit on vectors, you won't really be dealing with vectors in this sense anymore. You won't really have to worry about writing out all these different components. You'll have to know if something's a vector because it will determine how you approach it later on. But I know this seems very tedious, but it's good to know. So I'm just going to write down, kind of recap here. Our position vector was r, and that is x in the I hat direction plus k in the j hat direction plus z in the k hat. And then our velocity was the derivative of position, so it's dx by dt. Well, I'll just write it like this, dr by dt is what we start with. And when you take the derivative of that vector r, you get velocity, the x component of velocity in the I hat direction, plus the y component in the j hat direction, plus the z component in the k hat direction. And then acceleration is a derivative of velocity with respect to t. So if you take the derivative of our velocity equation, you would have acceleration in the x direction, I hat, plus the y component in the j hat direction, plus the z component in the k hat direction. So that's just to get us started talking about 2- and 3-dimensional motion, just so you're aware of how the coordinate system is set up, how we talk about vectors in these 3 dimensions, and just the basic notation. And next time we will start talking about the equations of motion in 2 and 3 dimensions, and we like to call that projectile motion, so that's always fun. All right, guys, I hope you got something from this. If you have any questions, please let me know, and I will talk to you guys next time. Thanks. Hi, everyone. Welcome to the Interested Reader Podcast. This is episode 10, which for me is a big deal. I didn't think I would actually do this many, but here we are. And I like the number 10. Any round number or multiple of 5 is one of my favorites. 2 is my favorite number, if anybody's counting. So I wanted to do an episode, finally, about astronomy, because that is why I got into physics and astronomy and teaching, and why I'm doing this podcast is because it all started with me having this interest in astronomy. I don't know if I've told the story about how I got into astronomy, because it was never like a lifelong thing. It just kind of happened out of nowhere. And we're going to talk about stellar evolution today, which is one of my favorite topics. So it's how stars are born, how they evolve, and how they end up dying as supernova. And it's supernova 1987A that got me into astronomy. And I had never really been interested in astronomy. It was always life sciences for me. I was really good at biology in high school. I'd always wanted to be a marine biologist or a veterinarian. In high school, I thought maybe I'd go into genetics, but I wasn't really sure which field. I'd wanted to do marine biology and go to La Jolla, California. The school out there is Woods Hole Oceanographic Institute, and it's a very good, prestigious school. And maybe I could have gotten in. I mean, I was a straight-A student in high school as valedictorian, but out-of-state tuition was insane, and there's no way I was going to be able to afford it, and I didn't have any help from my parents, so there's just no way I could afford to go out of state. So I had a full scholarship to stay in-state at Florida, and if I was going to go to Florida, there was only one school, and that was UF, the University of Florida. So they didn't have a marine biology program, and of course my parents were like, why don't you just go to another school that does? Southern Florida had one. I mean, there's all sorts of schools all over Florida that have marine biology programs. But I was too stubborn. I'm like, no, I'm going to UF. If it's anything in Florida, it's got to be UF. So they didn't have marine biology, so I was like, well, I'll just major as biology, and then I can specialize as I go into grad school and all that. So during college registration, the last month or two of high school, I go to UF, register as a biology major, everything's kind of set. And then in that last month or two of high school, we're kind of coming up to the end of our textbook, which was a college level biology book. And they'd mentioned about how stars explode into supernovae, and they release all of the heavier elements that we see in the universe that actually then condense and reform and make up all the matter that we see. And there's a picture of supernova 1987A, and I was just enthralled by this picture in this textbook. This is a biology textbook. And I just thought, I want to see one. And I didn't know if you could actually major in astronomy. It seemed kind of weird to me, because it didn't seem like anything that I could do. So I was like, I don't know, I think people can do this. I think they major in astronomy. And so I looked, and UF did have an astronomy major as a program. So, my last month or so of high school, I changed my mind and went, I'm just going to go study physics and astronomy, which no one in my family or friends could understand. I mean, I didn't really understand it. I was like, I don't know, I like looking at the stars, and Hubble telescope images are awesome, but yeah, that was about it. And here now I'm going to dedicate my life to physics and astronomy from this one picture I saw. But, so I majored in it, and I don't know if it worked out, but it was fun. It was very hard, but it was fun. So, in honor of my 10th episode here, we're going to talk about supernova 1987A at the end of our, kind of discussion here of stellar evolution. Okay, so we'll get started, and the first thing that we're going to pull up here is this really cool infographic from the Chandra website. So the Chandra X-Ray telescope is a very popular telescope, and it only takes images in the X-ray spectrum. And another kind of funny story about this, when I was in grad school and I was finishing up my master's thesis, and I had to give, part of the requirements is that grad students have to give a seminar to the students and faculty in the department. Every week, the astronomy department has a seminar, and at some point as a grad student, you have to give one of these seminars. So, and usually it's whatever research you're working on. So I'm presenting my research that I'm doing, and this is the research that's going to very shortly be counted as my master's thesis to get my degree. So I'm presenting it, and part of the data that I'm looking at is what I don't even remember the letters that they use, but it's a color spectrum of a star. So you take a picture of a star in all the different wavelengths: ultraviolet, violet, blue, red, visual, X-ray. So you get all these different brightnesses. It's a magnitude, and it tells you something about the color of the star and the brightness of the star and all these things. And so part of my data as I was going through was describing the magnitude of these stars in the X-ray spectrum. And one of the professors stops me and he says, "Well, good luck trying to get a magnitude of a star in the X-ray spectrum." And I was stunned. I was standing up there in front of all these professors with one of them telling me that I couldn't get X-ray data from a star. And I didn't know if he was he joking? Was he testing me? I had no idea. So I'm just standing there like a deer in the headlights. The data that I have isn't mine. I didn't collect it. I'm just reporting on what other degreed, PhD astronomers have collected. They've got the data in the X-ray spectrum. And there's a telescope dedicated to it called the Chandra telescope. And so I'm just standing like, I don't know how to answer this guy. Like, is he joking? Because what I want to say is, are you freaking kidding me? Like, where have you been? What are you doing here? But so I'm just standing there paralyzed with, like, what do I do? What do I say to this guy? So finally my advisor steps in and is like, well, we've got the Chandra telescope. We've got the X-ray data. And then the guy was like, oh, okay, yeah, right. Yeah, I forgot about that. And I'm just like, oh my God, can I just get out of here, please? Can we just end this right now? So yes, we can get spectra in the X-ray spectrum from the Chandra telescope. So what we're looking at now, if you're watching, is a really cool poster that they put together of stellar evolution. And so what we do is we're starting with a cloud of stellar dust and gas. And so throughout all the universe, there's just big clumps and pockets of dusty materials, just like very fine particles of gas and dust. And it all just kind of floats around. And eventually, if enough of it kind of accumulates together, the gravitational force pulls together little clumps and pockets of this dust and gas. And as they condense, they start to heat up. So you get the gravitational pressure pulling everything together, heating everything up, and you end up with what is called a protostar. So it's in the middle here. So once you have a protostar, there's basically 4 different paths that you can go. First, if you have a star that starts out smaller than the sun, so what we're going to do is most of our masses we're going to talk about as solar masses. And that means how many times the mass of the sun is the star. So one solar mass is the same mass of the sun. 10 solar masses would be 10 times the mass of the sun. So if you have a star that starts out less massive than the sun, I think they measure down to even 0.08 solar masses. So nothing really happens with the protostar, kind of just becomes this brown dwarf off here on the left side of the screen. If you're a little bit smaller than the sun, probably in that 0.1 range, maybe 0.5, you end up over here on the right as a red dwarf. So I don't want to say they're not exciting, but you don't get into the fusion of stars. You don't get the big explosions and all the fun stuff. So those are your two cases. If you're much smaller than the sun, you go brown dwarf. If you're just a little bit smaller than the sun, you go red dwarf. If you're roughly the same size as the sun, we call that a solar-like or sun-like star. And then the protostar follows this track off here to the left. So we have a sun-like star, and we'll get into the details of what happens here, but basically you are burning hydrogen in the core, and you just go through fusion, like nuclear fusions going on in the center, just like normal, no big deal. And then eventually you end up going as a red dwarf, a red giant. Once all the nuclear fuel is used up, it expands into a red giant. The material from the outer layers of the star, kind of in its atmosphere, get blown off, and it forms a shell around the inside core of what's left of the star, and that shell is called a planetary nebula. And then if there's enough mass in that central star, it will collapse down into a white dwarf. And if a lot of times these dwarfs are parts of a binary star system, so as the white dwarf rotates around its other star in that system, gravitationally it will pull matter from that star, and eventually it can accumulate to the point where it gets to 1.4 times the mass of the sun, so 1.4 solar masses. And if that happens, then that white dwarf can actually explode into what's called a type 1a supernova. So this is the path that our sun is predicted to follow. It should spend about 10 billion years in the current sort of nuclear fusion state. It's called the main sequence that it's on right now. And I think the age is estimated to be around 4.5 to 5 billion years. So our sun's got about another 5 billion to go. And then it will go, supposedly, the theory is that it'll go red giant, then planetary nebula, and then white dwarf. Now our sun isn't part of a binary system, which is weird. That makes it a kind of a rarity in the universe. Most stars are binary systems. And there is some speculation that we do have a binary partner. If you guys have ever heard of like Planet X, kind of this mystery planet that comes to the solar system, and everyone gets all riled up about it. But there is some indication that perhaps there is something else out there, and it's just a very slight wobble in some of the outer planets' orbits. It's just it would have such a long period that we just have never seen this binary partner in our solar system, because it is fairly unusual for stars to just be a lone star with its solar system around it. Alright, so going back up to our protostar, if it is much larger than the sun, so we're probably talking around like 10 solar masses, then the protostar is going to go into a supergiant. It'll typically start as a blue supergiant. And then there's a couple different tracks here. So blue supergiant will kind of bypass some of these other stages and essentially just go right to a supernova or a black hole. So the thing about blue supergiants is that they are very massive, they're very hot, and a lot of times they are known as the rock and roll stars because they live fast and die young. So they're rather short-lived. So if you are a blue supergiant, and if the mass is 100 times more massive than the sun, it'll pretty much just go right into a type 2 supernova. It's so unstable. And then if it's more than 150 times the mass of the sun, it goes basically from blue giant into a black hole. And there's just so much mass and so much heat generated that it can't stabilize into a star for very long, and it'll just collapse. So if you're going to do more than 10 masses of the sun, if you go blue giant, so you're right around that 10 mass, not anything too crazy. Eventually then you can go into a red giant phase, And we'll talk about all this on how this works on the different diagram of how stars evolve. So then from a red giant, if you use up all the nuclear fuel kind of right away with no sort of intermediate steps, you'll go into a type 2 supernova. That's what supernova 1987A is. Or if the other option for the red giant at this stage is that you can blow off your outer layers of the star. It can expand more because there's less mass, so it expands, it heats up. You can become a blue giant, and once again go into a supernova, type 2 supernova. And then from type 2 supernova, depending on how, doesn't matter how you got there, if there's enough mass left in that central star, the core will collapse into either a neutron star or a black hole. So this whole evolutionary chart is based on the mass of the star. So our sun is never going to be massive enough to go into a blue giant or into a type 2 supernova, or to create a black hole or a neutron star. It's going to do a white dwarf and then potentially type 1a supernova if that white dwarf was able to accumulate enough mass. So this is the basic overview of stellar evolution. And we're not going to do a whole lot of the details about what goes on, at least not in this episode. Maybe in another one we'll get more into the details of how each of these phases works. So the next part, main section of stellar evolution, is what's called the main sequence. And this gets plotted on what's called a Hertzsprung-Russell diagram, named after the two scientists that developed it. So along the horizontal, or the x-axis here, if you're watching, I've got this thing on the screen, but along the x-axis we are going to plot surface temperature of the star and or the spectral type. So the spectral type of a star tells you basically how bright it is and where its spectrum peaks on the electromagnetic spectrum. So on the bottom here we've got our surface temperature, and one thing to notice about this on the HR diagram is that the temperature decreases to the right. So normally when we make a graph and we have our horizontal axis, it increases to the right. On the HR diagram, it's actually going to decrease to the right. So as you're looking at one of these diagrams, all the way over on the right, we have all this red portion here. You've got your M class stars. Everything over on the right is a cool star, and then as you go over to the left, where it's blue, those are hot stars. So in this diagram, the temperature at the hottest is around 30 or 40,000 Kelvin, and then at the coolest it comes down to about 3,000 Kelvin. And that's the surface temperature of the star. So our sun's about 5,000 or 5,700 Kelvin. And then on the y-axis here, we just have the brightness in solar units. So again, we're comparing it to the sun. So how many suns is it bright? The main thing that we're going to look at these guys is really just this temperature down here's the kind of the main thing that we want to look at. And so the spectral class down here is this O, B, and then we've got A, F, G, K, M. So those are they've added, I think, 3 more in recent years. Like in the past, I don't know, maybe 8 or, I don't know if it's been quite 10 years. But in recent years, they've added 3 more that basically classify the dwarfs. But the ones that you're going to see mostly are going to be O, B, A, F, G, K, M. And in introductory astronomy, in the first class that I took, the mnemonic that they use, and this is just universal among astronomers, is O, be a fine guy, kiss me, or girl. And that's stuck with me my whole life. And one time when I was going into a coffee shop, so I was at the University of Iowa, so I'm in grad school at this point, and we have a fairly small astronomy department here. And I was going into a coffee shop, and there's a car parked outside, and its license plate is O, B, A, F, G, K, M. And I'm like, there's no way that's not an astronomer. No one else is going to pick that set of letters in that order. So I almost walked in there and was like, who's the astronomer? But I didn't. But it was just kind of fun to see it. And I'd seen that car around a couple times. And I was like, who is it? Because I must know him because there's not that many people. And it was a fairly nice car, so I figured it's probably a professor. But, so that was cool. I'd never seen anything like that before. I'd never seen anybody put that on a license plate. So that's how we remember the spectral types of stars. O's are going to be the hottest. Those are your big blue giants. M's are going to be the cool dwarf stars. And then our sun is actually a G-type star. So we're kind of in the middle. So if you look at this HR diagram that I've got on the screen, I like this one because it's got actual stars in it. A lot of times you'll just see a scatter plot of just black dots. But this one actually gives you some stars that we all have probably heard of. So here's our sun is right in here in the middle, this yellow part. And then we've got Alpha Centauri's pretty close by. We're going to talk about that one a little bit later. Some of our giants up here, the red giants, Aldebaran. That is the eye of the bull Taurus. We've got Arcturus. That, I believe, is the constellation Boötes. I know Arcturus because if you're looking at the Big Dipper, and the handle of it makes an arc, and so you can follow that arc to Arcturus. So if you just extend the line of that arc of the handle of the Big Dipper, the next brightest star you come to in the sky is going to be Arcturus. And then this other little giant down here is kind of in the yellowish, reddish areas, Pollux. And that is one of the twin stars of the constellation Gemini. So when you find the constellation Gemini, the two brightest stars that you'll be able to see are going to be Castor and Pollux. And Pollux is here in this kind of yellowish giant category. Up here in the very right corner is Betelgeuse. That's a large red giant, and we'll talk about that one. Actually, a super giant. So we'll talk about that one a little bit later. And Betelgeuse is in Orion. And let's see here. So the main sequence is this stripe that kind of runs diagonally through the car or through the diagram. And I'm going to get to the main sequence here in just a second, but I wanted to go through some of these other stars because most people, I think, well, maybe you haven't heard of these. Vega is a pretty popular star. That one is the loudest, I think, radio source. I think that's the one in the movie Contact that they heard, that they got their signal from. And of course, Contact had just come out when I was getting interested in astronomy in high school. And so of course everyone was like, oh, you've seen the movie Contact. Like that was the only reason I was going to go into astronomy, was because this movie. And I had to be like, well, yes, I have seen it, but that's not why. But yeah, everyone thought that's why I was doing it. So a couple of stars, I'm trying to think. So the summer triangle is going to be coming up soon. And some of the popular stars in that one are Deneb, up here in the supergiant category. It's almost a blue giant, a blue supergiant. Deneb is in the, I hope I get this right, it's in Cygnus the Swan. It's the brightest one there. Another blue giant here is Rigel. Sorry, it's going to be a blue supergiant. I mean, I think that one's in Betelgeuse. It's in Orion as well. Rigel and Betelgeuse are both in Orion. And we'll see that one later. Let's see. So we've got Deneb. We've got Altair down here, kind of close to where the sun is. Altair is in the constellation Aquila, the eagle. And I'm trying to think of who the last one is. It's in the constellation Lyra, the last star of the summer triangle. I don't remember. So let's see, we got our sun. Oh, Polaris here. This was the other one I wanted to say. So Polaris is kind of in between a giant, supergiant category, like an F or G class star. And Polaris is the North Star. So to find the North Star, it's actually not that bright visually for being the North Star, the guiding star that we're all supposed to be able to find and follow. It's not that bright visually, but if you go back to the Big Dipper and you see the 4 stars of the bowl, and you take the 2 bottom stars and just make a straight line from those 2 and just keep going straight, the next brightest star that you come to will be Polaris, the North Star. Again, it's not all that bright. And then the white dwarfs, we've got Sirius B, which is going to be the partner to Sirius A, and Sirius is one of the brightest stars visually in the sky. That is also called the Dog Star because it's in the constellation of Canis Major. It follows Orion. So yeah, I just really like this chart because it's got all of the different stars on it. It's kind of fun to see where they all fall. And kind of a comparison. They're kind of, I don't know if it's exactly to scale, but they kind of do a little bit of a scaling, so you can see. Our sun's pretty small. It's sitting here, you could kind of miss it. Okay, so that's the HR diagram. It's very popular when you're talking about stellar evolution, and it's one of the first things that you'll ever learn about when you take an astronomy course. And I've always loved it. I just love the fact that the stars are very predictable in how they change and evolve. And again, getting into that, now we're going to talk about the main sequence. So that, again, is this stripe that runs diagonally through the HR diagram. And it can range all the way from the O stars, the big blue supergiants, all the way down to the M stars, which are little dwarfs. And so any star, doesn't matter where you are in that spectrum, the O through M spectrum, you can be on the main sequence. So what's going on in the main sequence is you're at a point where you're just starting to form as a star. So you've got your protostar. It's accumulated the matter from your dust cloud. And it starts to heat up as it condenses. And eventually the temperature in the core will reach about 10 million Kelvin. And at this point, that's enough to start nuclear fusion. And it's a process called the proton-proton chain reaction. So this is where you're going to start fusing hydrogen into helium. And hydrogen is the most common element in the universe. So new stars have mostly hydrogen in them. That's what's out there. And then they fuse all that into helium. And if you're thinking ahead, helium is the second most abundant element in the universe. So at this stage, when you're just burning and you're fusing hydrogen into helium, it's pretty stable. So your nuclear fusion that's going on in the core is balancing that inward gravitational pressure, because all that matter, all that mass wants to pull into the center of the core. And the nuclear fusion that's happening produces enough radiative pressure to balance that gravitational inward pull. So stars are very stable at this nuclear fusion stage. And this state of equilibrium, it's also called, I want to say it's hydrostatic, but I'm not sure. But it's this state of equilibrium that is known as the main sequence. So whether as a protostar you started out very small, or you started as a big huge giant, at some point you reach this stage of equilibrium, and that is the main sequence. So the time you spend on the main sequence is determined by the mass of the star. Mass is kind of the determining factor for almost everything with a star's life. So a low mass dwarf star can burn hydrogen very slowly, and it can be hundreds of billions of years on the main sequence. And one of those dwarf stars is Proxima Centauri. That is our closest star, to our planet here. And on the HR diagram, if you look, it's way down here in the corner. So this is a picture here of Proxima Centauri. And if you're just looking at it, if they didn't label it for you, you'd have no idea where it is. The big, bright, blue-white star is Alpha Centauri. So that's the brightest star in this group. But Proxima Centauri is the closest to us. And it's closer to us than Alpha Centauri by like 0.2 light years. So it's not a whole lot. But Proxima Centauri is circled down here in the corner. This little, very tiny red star. So that's an example of a red dwarf. Very low mass. will probably just sit on the main sequence essentially for its whole life. And then just a close-up of the actual star itself is this right here. It just looks like a big starburst in the sky on this image. And this is one thing about observational astronomy that, I mean, I liked it because that's what I was going to study. So for whatever reason, I was interested in this weird stuff. But most people are not going to be very impressed with observational astronomy. Not that you can do on the ground with the telescopes that we have on hand, because they usually just end up looking like this picture here I've got on the screen. So this is Proxima Centauri, but it looks like just a bright overexposed picture. I mean, it's not that impressive to look at. And when I was in grad school, we had open house observing nights at the university. And as a grad student, part of your duties were to host one of these nights. So I think we did it once or twice a week. It may have even been more. But so, I was on duty to do this for however many days. You just get scheduled. And one year, Mars was going to make its closest approach to Earth. And all the newspapers hyped it up. And they all show images from Hubble. The beautiful red planet where you can see the ice caps and the canals, and you can see what's called canals. It's that iconic image of Mars, the red planet. So this gets plastered all over the papers, and making its closest approach, come look at it through the university telescope. And I was dreading that night. I didn't get scheduled that night, and I did not volunteer to help out because I knew it was going to happen. And there was a line from the roof of the building where the telescopes are down 7 floors to the ground. And some of the TAs that were there said there's about a 3-hour wait, that people were in line. A lot of that's inside a university building, so you can't smoke. And people got pretty ornery by the time they've waited 3 hours to go look at Mars, making its closest approach. So they get to the telescope and they look at it. And it looks exactly the same as if you were to just stand in your yard and look at Mars in the sky. Because the telescopes we have here, and at least at the university, they're just not that good. It's not the Hubble. That's what everyone was expecting to see. They were expecting to see that iconic image. But the closest approach, it just isn't changing visually what the planet looks like. Now, astronomers get excited about it because, it is kind of cool that it actually does come a little bit closer. And if you're into the very nuanced mathematics of orbital mechanics, then that it is kind of a big deal and it is cool. But that's not why those people were lining up to see it. They wanted to see the picture. They wanted to see Mars. And it didn't look any different through the telescope than it did just naked eye looking from your backyard. So I'm glad I wasn't there to deal with that, because I heard that there were some pretty angry people. I mean, that's a long wait for that, but it's just the way it got hyped up, and I was just like, please don't say that, because it's not going to look like that. People are going to wait, and they're going to be so disappointed, and they were. So I don't mean to be a wet blanket on astronomy with that. Just observational astronomy, just unless you're using the telescopes. I think it's cool, and I'm still going to be trying to get my son interested in it. But just be aware that you're not going to look through an ordinary telescope and see pictures like from the Hubble or from the James Webb telescope. But so this is Proxima Centauri here. Again, just looks like a bright overexposed picture, but that's what it is. Okay, so those are our low mass stars. Another example of a low mass star, if you guys remember from one of the early episodes, was the TRAPPIST-1 star system. So one of the stars in there, they've got some dwarfs. I don't know how many, but so here is an artist impression of the dwarf. The main reason I wanted this one was because I was going to show you guys a picture of the telescope. But so if you remember that the TRAPPIST one was the musical system that they'd put sound to, and it was found to be one of the most musical systems because of the way the things orbited, and just the the cadence and the way they were orbiting, they were able to put together as just this musical sound. What I wanted to show you here was the telescope that they used, which is this monster here. And here is a lady standing next to it. So this is Dr. Susan Lederer next to the Euclid telescope in Mauna Kea on the island of Hawaii. So this is what they used to find that TRAPPIST star system. I mean, look at this thing is gigantic. And these are all just mirrors and light detectors and collectors. And I think this little piece right here, if you can kind of see with my cursor, I'm kind of circling it here. I think that's the eyepiece where you... I don't even know if they would have eyepieces on this one, honestly. It'd probably all just be digital. But I mean, look at the size of this thing. Just so we can go look at some stars. That's crazy. But stuff like this is one reason I'd gotten into astronomy. Because I mean, I think the equipment is just so cool when you get into it. I always liked when we had an observational astronomy class going out to the observatory, and I mean, we didn't have anything like this, obviously, but just setting up the telescope and collecting the data for your images. I thought it was fun. So anyway, that's just a telescope that they use to detect some of these very cool, dim dwarf stars. Because you need to sit there and collect a lot of light for them because you just can't see them, so you got to sit there for a long time and just collecting photon by photon until you see it. Okay, so next on the main sequence is going to be our solar mass stars. So let me just click back here. So here's our HR diagram again, and so our solar mass stars are in this kind of orangey red area, so our sun's right here in the middle, kind of in the yellow G spectrum. So these stars will spend about 10 billion years on the main sequence, and the sun's about halfway through. And so another example of this is Alpha Centauri. So again, we talked about them. Alpha Centauri being the brightest star in that constellation, or in that area, at 4.3 light years away. So here is Alpha Centauri is on the left, and the other star, if you look in the image here on the screen, the other bright spot on the right is Beta Centauri. And so these are both binary star systems. So Alpha Centauri is over here in the left, and then again circled in red is Proxima Centauri, that little one. So Proxima is the closest, Alpha Centauri is the brightest. And Alpha Centauri again is a solar-like star. And then this is a picture of the sun in different wavelengths. So the red part of this picture is ultraviolet light, and then at the top you see these blues and greens and yellows. That's X-ray radiation. So they just overlaid two different exposures, one in ultraviolet, one in X-ray. And there's so many of these pictures of the sun. If you guys go to the, it's called the SOHO website, Solar, oh my gosh, I'm going to get it wrong. Solar something and Heliographic Observatory. And they just take pictures through all the different spectrum. You can find them in different wavelengths, and it's really cool because then they'll put together pictures where the sun's blue, where it's green, red, and it's really cool. And each spectrum tells you something a little bit different about what's going on with the sun. But I like this one because of the overlay, where you can see some of the bright X-ray emission at the top. And the Solar Dynamics Observatory is another one. That's operated by NASA. I think SOHO is operated by the European Space Agency. So that's the sun. Our last option for the main sequence is basically your very massive stars that only spend a few million years. So those are your giants, your blue and your red giants, your rock and roll stars. So a couple examples of those in Orion are the giants Rigel and Betelgeuse. So this is a picture of Orion. So this is taken in the optical wavelength plus hydrogen alpha. So you can really see those gas clouds, which are the red clouds in the picture. That's all hydrogen gas. So Rigel is up in the upper left corner. That's the red guy up here. I'm sorry, that's Betelgeuse. Right? Betelgeuse is the red supergiant. And you can actually see it when you go out and look at the Orion in the sky, you can see a little bit of a red tint to Betelgeuse. It's obviously exaggerated in this picture, but you can tell that it's a little bit different color. So that's Betelgeuse up here in the upper left, a red supergiant, and then Rigel is down here in the lower right corner, and Rigel is a blue supergiant. And this is just a close-up picture of Rigel, so it's obviously the brightest part here. And I don't know if we got one. So this is Betelgeuse here. Again, it just looks like almost, you can't tell much difference between that and Proxima Centauri. And Proxima Centauri is a dwarf star. But again, observationally, you just take a picture of them both. They kind of both just look like just bright stars. So that's basically our life on the main sequence. It can be any star from your supergiant down to your dwarf. The characteristic of being on the main sequence is that you are in this state of equilibrium where the nuclear fusion at the core is balancing the gravitational pull and the gravitational collapse of the outer layers. So it just sits in this nice state of equilibrium. So what happens when that balance no longer applies? This is when you start to get kind of the action of evolution. So, and we kind of touched on this before, that a star can either cool to a brown dwarf if the protostar was not very massive. To go back to our evolution chart, if your protostar was pretty small, after the main sequence, it'll just kind of move over into the dwarf stage and just kind of sit there and cool down. Or red dwarf too. If it's just a little bit smaller than the sun, you'll go red dwarf. If your star was the same size as the sun, after your main sequence balance, you'll go red giant, then planetary nebula, white dwarf. Potentially the white dwarf could collapse later. If the protostar was much larger than the sun, after your equilibrium phase on the main sequence, even if you're a blue supergiant, you'll likely turn into a type 2 supernova, and then the core will collapse into a black hole or a neutron star. So that's after your main sequence. So the next thing we're going to talk about here will be supernovae, since that was the main thing that got me into astronomy, was supernova 1987A. And I'll put all these links here, this link to the stellar evolution chart on the show notes. Alright, so here is, we'll get to this in a second. So just briefly, what is a supernova? So we've talked about it's the explosion of massive stars. And if the initial mass of the star, when it's born, that protostar, is much greater than the sun, it'll end up as the type 2 supernova. So that's where you have your blue giant that ends up going into a type 2 supernova. If the initial mass is less than the sun, or roughly the sun mass, it'll blow off its outer layers, you'll get a planetary nebula, and then that inner core can collapse into a type 1A supernova. Now that only happens if that white dwarf does accumulate enough mass, that 1.4 solar masses, to collapse into the type 1A. It's not guaranteed to happen, but that's how it would. So supernova 1987A. This is a type 2 supernova found in the Large Magellanic Cloud. And the Large Magellanic Cloud is a satellite galaxy of the Milky Way, so it's our closest galaxy to us. It kind of orbits with us, almost like a binary galaxy system. So this is a picture of the Tarantula Nebula. That's this bright looking thing here. And this, if you come over here a little bit to the right and down, this bright star kind of in the middle of the picture, that is the supernova. So when I say SN 1987A, that is the nomenclature used. So SN means supernova. It was discovered in 1987, and the A designates that it was the first one discovered that year. So It's approximately 168,000 light years away. And this was the closest supernova since Kepler's supernova in 1604. So Kepler's supernova was a type 1a. It's a picture here of it. And it was in the Milky Way galaxy, and we haven't seen one since. And this was in 1604. And so SN 1987A was the closest one since this one, which supernova 1987A happened in the Magellanic Cloud. This supernova remnant here, Kepler supernova remnant, what happened in our Milky Way. And the picture here is X-ray, optical, and infrared. So again, you take a picture of this object in all these different wavelengths, X-ray, optical, infrared. You put them all together to get these pictures like this. So in case you guys didn't know, almost every image that you'll ever see of a space object is what we call a false color. So they've taken pictures in different wavelengths. Usually it's your standard RGB, red, green, blue, if you're going to do visual. And then they will take pictures in your X-ray, your infrared, your ultraviolet, and then they'll just put them all together. And a lot of times everything's taken in black and white. And then they kind of assign colors, but they have a system for it. So when you go in the lab, you can take a tube of hydrogen gas and you can ionize it, and you'll see that it kind of glows red. So whenever you see hydrogen, and they know what wavelength this happens at. It happens at a very specific wavelength. So you can go out in space and you can look around, you can find this wavelength. So when you see that wavelength, you know you're looking at hydrogen. And because you've ionized it in the lab, you know that it glows red. So you can color that wavelength. Anywhere you see it in your image, you color it red. And you can do the same thing with nitrogen, oxygen, all the elements. So most images are taken in black and white, and then they're colorized in processing in a lab. I think Hubble's Wide Field Planetary Camera 2, also called WIFPIC 2, I think might actually take optical images. And there are, Hubble does take some. I think it's probably with that camera. James Webb might take optical pictures now. But for the most part, not much happens in our optical spectrum. It's a very narrow part of the electromagnetic spectrum. So stars do a lot of stuff in X-ray, infrared, UV, all the stuff that we can't see. So they just take them in those wavelengths, take pictures of those wavelengths, and put them all together. So this is a picture of what would be a type 1a supernova. Alright, so this is the picture that I saw in that textbook that got me into astronomy. This is supernova 1987A. So the picture in the inset here is a close-up, a zoomed-in image. It's actually overlaid in this big red image too. I don't think that anyone's ever actually taken a picture where you have the nebula cloud with the supernova right in the middle that's that detailed. If you're taking a picture of that nebula or of the gas cloud around it, I don't think you're going to see the supernova that detailed. So I think this is actually a composite as well. But this is the one I saw, and my friend actually bought me a really nice print of this because she knows my favorite. So what we're looking at here is the remnants of a blue supergiant, and it was named Sanjalik -69202. So -69 is its position in the sky, called declination. 202 means it was the 202nd object in this catalog. Sanjalik was the guy who found it. So Sanjalik -69202 was a blue supergiant that exploded, and this is the remnant of it. And because it was a supergiant, a blue supergiant, we know that it was a type 2 supernova. Now, at the time, in 1987, it was thought that only red supergiants could produce supernovae. They didn't think that blue supergiants basically lived long enough. I'm not entirely sure. I couldn't find out exactly why, other than that they are too hot. So over on our HR diagram, they're way over on the left, and there's 30,000 Kelvin here's where on your main sequence here you start like 60 solar masses. And so they thought that they were too hot and they would just burn out, and they couldn't actually be stable enough to basically to live long enough to do this core collapse and to produce a supernova. So it was SN 1987A was a bit of a mystery because the star that was that exploded, they're like, well, it was a blue supergiant, but that can't be because they can't go supernova. So they have high luminosity and high mass loss rate. One thing that we haven't talked about, but there is a thing called a solar wind. So as stars are burning, like mass is just constantly being ejected from stars just into the what's called the interstellar medium, outer space. And the hotter and brighter a star is, the more it's like burning off and blowing off all these outer layers. And blue supergiants, being as hot and massive as they are, they're just constantly kind of spewing this matter, and their solar wind is very strong. Stellar wind. Solar wind would apply just to our sun. Their stellar wind is very strong, and so you're constantly like stripping matter away from the star because it's so hot. So scientists didn't think that it could retain enough mass to collapse into a supernova. But it's now been found out that yes, they do, and it happens, I don't know if I'd say frequently, but it's well known enough. We've seen it enough times now that we're like, okay, blue supergiants can go supernova. So one of the classic things about supernova 1987A are these three rings. So you get this really bright ring around the center, and then these two red ones, kind of diagonal here. And so what's happened is when the star was exploding, before it actually went supernova, it blows off the outer layers of its atmosphere. So as a supergiant, it kind of releases all of that atmosphere as it's getting ready to collapse. So all that matter, all that, the plasma, the gas, everything that's making up that star is now been ejected and is just expanding away from the center of the star into space. And then eventually the core collapses and explodes, and that shock wave then moves out through the center, or from the center of the star, and it moves out through all of that outer atmosphere material that was ejected earlier. And that's what we're seeing here with these bright rings. As that shockwave interacts with that material, it ionizes it, it can condense it into clumps, and we see that bright orange ring around the center. And these two bright spots, I think, are just background stars. They just happen to be positioned pretty cool in a neat way. So this is a picture of that inner ring. So here's our X-ray on the left, that's taken with that Chandra telescope. And then Hubble Space Telescope optical here is on the right. And you can kind of see there are these like it's a ring of like clumps of material, so it looks almost like a pearl necklace. That's what I think they've called it. And so that's just as that shockwave moves through that stellar material that was ejected earlier, it interacts with it, it clumps it, it ionizes it, and you see this ring of material. And this picture here was taken with the James Webb telescope. I couldn't find a date on it, but the James Webb got into orbit in 2022, so this would have been taken in the past couple years. And I couldn't find any information if it was an overlay. It looks like it would have to be because the inside's kind of this nice blue color. But you can still see that there's some of that ring of, clumps of material in a nice ring. That ring is projected to dissipate and to finally disappear sometime between now and 2030. As that shockwave moves farther and farther away from the central star, everything will finally dissipate and we just won't see it like this anymore, and that ring will disappear. And then this is just a before and after picture of the Large Magellanic Cloud. So on the left here is our before picture, and let's see. I'm trying to see where, because you see what we're looking at is going to be in this corner up here. I'm kind of circling with my cursor if you're watching. But this is the Tarantula Nebula. It's kind of a brighter spot here. And to the lower right, in the picture on the right, you see there's nothing there, or it's a very small white dot. And then after the supernova, you look in the picture on the left here, Tarantula Nebula, and you'll see this very bright white thing is new there. So that's the supernova. Again, it's very hard to see, and doing observational astronomy this way, where you're comparing images over the years, can be tedious. I did some of this as an undergrad, where we were trying to look at it's called active galactic nuclei. So you look at the centers of galaxies, and you see if they've increased in brightness at all. And then if they have, that'll tell you that there's something going on, in the center, and you can look into it. But you're basically just comparing images. Like, here were images taken 5 years ago. Here's our images taken, last year, and then you compare them and you see, was there any change? And so you have to. It's kind of fun because it's data analysis, it's image analysis, where you align the two images, and then the computer can detect differences in the brightness of the images. And it was interesting, but yeah, it's very tedious, which I think will bring me to my last thing here. Oh, those are all, we don't need that. So the last thing I want to leave you guys with here is one of my favorite clips from The Simpsons. I think it encapsulates science perfectly. So hopefully I don't get a copyright infringement here and you guys actually do get to hear this. But let me just play this for you. This is called Bart's Comet.
There's nothing more exciting than science. You get all the fun of sitting still, being quiet, writing down numbers, paying attention. Science has it all.
Is that the telescope we're going to be looking through?
Yes, but you won't be looking through it.
Alright guys, that was one of my favorite things. Science has it all. Alright, I hope you guys enjoyed this episode. I'll probably do some more later about maybe some more detailed stellar evolution stuff, because it's one of my favorite topics. But until then, guys, I will keep you in mind, and let me know if you want to talk about anything. If you want a specific topic, you're interested in something, you have more questions about anything I've talked about in any of the episodes, let me know. Otherwise, I will talk to you guys next time. Thanks. Bye. I hope you enjoyed this episode and are inspired to question and investigate the world around you. Let me know what you're thinking about. You can contact me through the website, theinterestedreader.com, send me an email at sarah@theinterestedreader.com, or join the Interested Reader group on Facebook. I'll see you at some later time T, where T is greater than T naught, and T naught is equal to now. Thanks for being an interested reader, and I'll see you next time.